Welcome. In the last two video lectures, we discussed about Taylor's approximation theorem, and we used it to linearize functions, and then we used it to linearize dynamical systems at equilibrium points. Here, we will do one more exercise. We'll take it from the beginning, so we will derive the differential equations of the system, and we will linearize the system at an equilibrium point. And afterwards, we will discuss what happens when we have to linearize functions of more than one variable. So far, we have been focusing on functions, let's say phi of one variable. And by Taylor's approximation theorem, we know that if this function phi is differentiable at a point x0, then we can use the following approximation. And the question we will deal with in this lecture is what happens if we have functions of this form from Rn to R, for example, functions of n variables. But before we get there, this will be the second part of the lecture. Let us focus here and derive the differential equations that describe the system. Then we will linearize these equations. So here we have a dynamical system that is a mass transfer problem. We have some inflows and outflows. In particular, we have this f input, f in, which is an input variable. We have this f, which is constant, and we have the outflow from here. So we know from the mass balance, the basic mass balance equation, we know that the total inflow minus the total outflow equals the accumulation. Here the total inflow is f plus f in, of course. The outflow is f out, and the accumulation is density times the surface of this cylindrical tank times the rate of change of the level of liquid inside the tank. And equivalently, we can write this is not a linear function because we have the square root here. We have this nonlinear component. We have this function of h. H is a state variable. Let me write it in red. And f in is the input variable. So there are two reasons why this whole equation is not linear. First of all, we have the constant term. And second, we have this whole function of h, which is not linear. By the way, recall that a lowercase is the cross-section area of the orifice. So let us linearize this function. The question is where. It only makes sense to linearize dynamical systems at equilibrium points. So a pair actually, h equilibrium f in equilibrium, this is the state, this is the input, is an equilibrium point This pair is an equilibrium point of this dynamical system, equation number 1, if the derivative here vanishes, if this is equal to 0, and then if we replace here, if we substitute f in by f in e and h by he, the pair f in e, he must satisfy this equation. We don't need to solve anything here. You can plug in the specific parameters you might have in an application and determine such pairs fne, he. We're not interested in doing that now. We will use that afterwards to define deviation variables as we did previously. So now let us linearize this function phi here, phi h. We know the derivative of this function. This is a constant. Recall here that that this is the derivative of the square root. It is 1 over 2 times square root. And we have, of course, the coefficient 2 times g. These 2's, we can remove them. Very good. So this is the derivative of phi, and we can now linearize it. So phi at he plus the derivative at he. We're interested in linearizing at that point he. So we have where this value is the value of phi at he, and this value, that value over there, is the derivative of phi evaluated at he times this difference. Okay, so this is equation number 3 now. And we have now linearized the nonlinearity that is involved in our original differential equation. So I can plug in this approximation here, and I will obtain, I need some space on the whiteboard, I can write it up there. So the linearization of equation 1 becomes and that is the linearization of equation number 1. However, this is again not linear yet because it involves certain constant terms. For example, f is constant, which said that in the beginning, and this term is also constant. But we'll do the trick now with deviation variables. So I can subtract this equation and this equation that describes the equilibrium points. I will now write here. So let this be equation star, and let this be equation hash. So we have but let us write them again here, one under the other. Sorry, I meant before equation number 2. So equation star asterisk minus equation number 2. Actually, we can call that equation number 4. That is equation number 4. This is equation number 2. I have copied them here. And let us subtract one from the other. So we will have this term minus this term. These two terms are exactly equal to one another. These two terms again are equal to one another. And then we have and now we'll do the trick with deviation variables. So f in minus f in equilibrium, the difference between the input variable and its equilibrium value, is the deviation variable f in bar. We just define that to be so. We define a deviation variable for the input and one for the state variable, h minus h equilibrium. We see that it quite naturally appeared here. And now I can write exactly the same equation as follows. And we see here that we have an equation that involves f in bar, h bar, but we have h dot here. We have the derivative of h, not the derivative of h bar. But we mentioned in the last lecture that since h bar is defined like that, if we differentiate both sides, since he is nothing but a constant, then the derivative of h is equal to the derivative of h bar. So I can simply put a derivative here. and this is the linearized variant, the linearized approximation, the linear approximation of the original differential equation, which is equation number 1. So I can write it So of course the result is a linear differential equation. So it is a constant term times Fn plus a constant term times h bar equals a constant term times h bar dot. And these constant terms we can copy from here are 1. This number minus rho times a divided by the square root of 2ghe, and then we have rho times a uppercase. So this is the linearization of this original equation, which has this nonlinearity, has the square root of h. By the way, this is not a nonlinearity, this is the square root of he, which is a number. He is the equilibrium level of liquid, so this is in practice he is nothing but the point around which we plan to operate the system, and this is again a constant term, and this whole equation is a linear differential equation. So problem solved. So now the question is, what happens if we have a dynamical system that looks like that? Equation number 1 here, x dot is equal to x times u. The right hand side is a nonlinear function of x and u. This is not a linear system, of course. We have this function phi, which is a function phi of x and u. Therefore we cannot apply, this is not a function of one variable, therefore we cannot apply Taylor's approximation theorem, which applies to functions of one variable, at least the version of Taylor's approximation theorem that we stated in the last 2 video lectures. But we can use Taylor's approximation theorem version 2. Which states the following. Okay, this looks a little lengthy at first sight. Let's read the theorem. It states that if phi is a function of n variables that takes a vector of dimension n and returns a number, so it is a function like this one. Phi indeed takes 2 variables here, in this example, and returns one number, their product. So if this function has continuous partial derivatives with respect to x1, x2, xn in the neighborhood of x0, this whole sentence here means that our function phi is sufficiently smooth at x0 and close to x0. Then we have this approximation equation, which says that our function is approximately equal to its value at x0 plus, and it would be, in the case of one variable, we would have actually from here to here. That's the part with one variable. So derivative with respect to that variable times x minus x at point 0, x minus x0. But here we have, with respect to the second variable, with respect to the third variable, up to the derivative with respect to the last variable xn times xn minus xn 0. It is best to, okay, we stated the theorem, it's best to give an example, actually this example, to see how it works in practice and to understand the theorem as well. So let's go to that example. So the task is to linearize the system. Of course, when we talk about linearization, we must specify at what point we need to linearize, and it only makes sense to linearize dynamical systems at equilibrium points. So what is an equilibrium point of that differential equation of that dynamical system? So here a pair apparently a pair x0 u0 is an equilibrium point of that system if x0 times u0 is equal to 0, according to the result we stated in the previous lecture. If you look at it closely, this means that either x0 or u0, so either one or even both, are equal to 0. These are the equilibrium points of the system over here. We don't need to do something with this equation. This is equation number 2. We'll just keep it there. And now we have function phi. Let me write it again. X times u. Let's find the derivatives of this function. There is a derivative with respect to x. So it is the derivative of x times u, treating x as the variable and u as a constant. So in that case, this is equal to u. The derivative of that function with respect to u now, it is quite naturally equal to x. Now the derivative of function phi, the derivative of this function with respect to x is equal to u. The derivative of this function with respect to u is equal to x. Now the derivative at x0, u0, evaluated at x0, u0, is u0. I simply substitute here u0. And this is x0. So this is the function. This is the derivative with respect to the first variable. And this is the derivative with respect to the second variable. I can now use the previous theorem, according to which this function is can be approximated by its value at that point plus the derivative of the function with respect to x evaluated at that point, the derivative of phi with respect to x evaluated at x0, u0. Look here, I will write it with red. This is in red color now, with respect to x times x minus x0. And likewise, I'll do the same for the other variable. So x is one variable, u is the other variable. Now I just need to substitute here what I have. So phi at x0, u0 is apparently, and this is the linearization of function phi close to point x0, u0. And I need to write this actually. So this approximation makes sense for x and u close to x0 and u0 respectively. And now I can, of course, approximate this function. I can write the linearization. But this differential equation is not exactly linear. It is affine. It remains to do something to get rid of the constant terms. So x0, u0 is a constant term, u0, x0 is a constant term, and x0, u0 is again a constant term. And we will proceed exactly as we did in the last examples where we had just one variable. So we know that x0, u0 is equal to 0. Let me write it actually like that. I will subtract the two equations by part. So x dot minus 0 is x dot. These two are equal to one another. So x0 u0 minus itself is equal to 0. And then, but after that, what we do is that we introduce deviation variables. And if you look here, x minus x0 is x bar, u minus u0 is the new variable u bar, and x dot is the same as x bar dot. And we can now very easily be straightforward to write x bar dot is equal to u0 x bar plus x0 times u bar. And this equation over here is the linearization of x dot is equal to x times u at the point x0, u0, which is an equilibrium point of the system. So this is the answer. So now the last question, the last topic for this lecture is how to deal with systems, with nonlinear systems which are of higher order. For example, we have this system given by this equation, and we can identify, first of all, it is nonlinear because it involves terms like x times u and x dot squared times sine of x. All these are nonlinearities. So one would say, okay, why don't we define a function phi of x, x dot and u, which is such and such, and then we apply Taylor's approximation theorem for functions with several variables and blah blah, and we proceed exactly as we did previously. The thing here, the problem is that it only makes sense to linearize to linearize at equilibrium points. And in order to determine the equilibrium points of such a system, we need to write it in the form of a state space representation. So we should start here. We should do something about this second order term. This system, in other words, is not in a state space representation, but that's not a problem. We know how to deal with these situations. We define two new variables. x1 is x, x2 is x dot. This implies, x1 dot. And this is the system equations in a state space representation. Of course, if you very much like, now you can introduce a new state variable, let's say x underlined, which is x1, x2. And then you can say that x underlined dot is equal to this and that. So x underlined dot will be x2, this goes here, and this expression goes here. You can watch video lecture number 1, I think it was. So this is the state space representation. And we can now talk about equilibrium points. So not a pair this time. We can either say the state input of course pair x0 u0, but x is x underlined. This is the state of the system. X is not the state of the system. X underlined, which is a vector, the vector x1 x2 is the state of the system. So we're talking about rather the triple x1 x2. Let's call these x1 0 x2 0 u0. This is an equilibrium point. We can say that this is an equilibrium point. And I will now take the differential equations in state space representation, and I will set the derivatives equal to 0 to obtain the two equations. 0 equals, from here, 0 equals x1 0 u0 and so on, x20 squared. I will write it like that in parentheses to avoid confusion. So this is equation number 1. Let's say equations 2a, 2b, equations 3a, 3b, and these are equations 4a and 4b. So we have taken this nonlinear second order differential equation, we have written it in state space representation, and we have derived the conditions that are satisfied by its equilibrium points. It's now time to linearize equation number 1, and for that, to linearize equation number 1, of course, means to linearize the state space representation. Let us do the following. Let us just forget about this equation number 1. There is no equation number 1 anymore. It disappeared. So it's all about these equations now. Okay. And this is the nonlinearity we have. This is fine. This is linear. This is the nonlinear function. So the nonlinear function we need to linearize is function phi. And the objective is to linearize it at x10, x20, u0, which is an equilibrium point that satisfies these conditions. So what are the derivatives of function phi with respect to x1, with respect to x2, and with respect to u? With respect to x1, so I have x1 here, the derivative is u minus x2 squared. The derivative of sine is cosine of x1. Very good. So again, with respect to x1, x1 is the variable, so this is a constant. So u times x1, the derivative is u, and here this is a constant with respect to x1. So constant times sine, and the derivative of sine is cosine. For x2, we have, from the first part, we have 0, and we have minus sine x1 to x2, and then 2 times x2, and with respect to u, just x1. And now very quickly, so the derivatives at the equilibrium point are given by these quantities. These are now constant quantities. And now we have that the linear approximation of function phi is given by the following. It is this term, which is the value of phi at the equilibrium point, now these three multipliers here, these three terms, are the derivatives with respect to x1 at x10, x20, u0, with respect to x2 and with respect to u. So in particular, here, this term that multiplies x1 minus x10 is this term. This term goes here. This term, which is the derivative with respect to x2 at the equilibrium point, this part, must go here. And of course, this term goes here. So this is the linear approximation of function phi at the point x10, x20, u0. And I can take the differential equation, which unfortunately I erased, but it is the following. This is the pair of equations that I erased from the whiteboard. and then the second one is nonlinear, and I can replace this whole thing with this expression, which it looks lengthy, but it's rather simple because it is, imagine, number plus a number times x1 minus x10 plus another number times x2 minus x20 plus a third number u minus u0. And I will leave the following to you as an exercise. What I would like you to do here is to take this approximation and plug it in here so as to approximate the second equation, which is a nonlinear equation. Then subtract by part this equation by this one and introduce deviation variables. What are the deviation variables you need to introduce? Of course, they are the same as before. So you will need to introduce a variable x1 bar, a deviation variable for x1, x1 minus x10, and similarly. So introduce these variables. You can see here very easily, for example, that this one is x1 bar, this one is x2 bar, this is u bar, and so on. Now, once you subtract this equation with the approximation for the nonlinear part, you subtract that and that first equation, some terms like this one will just disappear, and the rest will give rise to deviation variables. So you will have taken, what we have achieved here is that we have taken a differential equation. The original one was, so in conclusion, like a summary of what we did here, we took this differential equation. We noted that it is a second order equation. We derived the state space representation of that. Then we determined the equilibrium points. We determined these conditions which must be satisfied for the equilibrium points. Then on the state space representation we identified some nonlinearities. We defined a function phi that describes these nonlinearities, and we approximated it using Taylor's approximation theorem for functions of several variables. So this is it. And then what you need to do is to plug this into your state space representation and have a linearized version of your nonlinear equations. And then we introduce, what we need to do in such exercises is that we introduce deviation variables that allow us to write the linearized equation as a linear dynamical system instead of an affine one, which involves constant terms like this one. So this is the whole procedure, pretty much this is like a summary, it's like a revision of what we described and what we discussed about in the last two video lectures, as well as in the beginning of the course. So that's it, fairly simple. Thank you very much for watching, and until next time, goodbye.